All right, hell yeah. Thanks for joining me. What we got here is a physics problem, and basically, in a nutshell, all we're going to do is set it up so we get the F equals ma part. That's the part I love, and that's what we need more of is just the F equals ma. Then what we're going to do is we're going to put it into Excel. You know what I mean? Because we have the F equals ma, what does that mean? We got the A part, we got the acceleration. In this case, it's angular acceleration, but that's fine. Hell, if we know the angular acceleration, that just means that's just the change in angular velocity. You know what I mean? Just like acceleration is the change in velocity divided by change in time. Okay, and we're going to do that. But we're going to take a look at this problem. What the hell does this problem even say? It says you have any sort of circle. This could be a sculpture, you know what I mean? And then you put something like a marble at the top of it and roll it off. Now, in this case, it's not rolling, it's just sliding. We're not doing any rolling. We're just doing particle dynamics with no friction. I bet you about the same thing if it was rolling up. It'd be kind of interesting. But at some point, it's just going to roll faster and faster, and then it's just going to launch off. Now, I don't think we need the whole circle. You know what I mean? Well, let's say it got to 90. It ain't a magnet. You know what I mean? It ain't just going to get sucked in. You know what I mean? So, uh, it's at least going to fly off at 90. Like maybe it's going so slow it can actually get up to like 90 degrees. That's not the case. I'm just going to give you the answer right here. The answer is 48 degrees. So hell, so not to confuse you, but there's 45. Because I was even like, oh, there's 45 right there. No, no, no. But anyway, so yeah, that's pretty amazing. About 48 degrees right there, it actually just flies off. And why do things fly off circles? Well, like let's just say this is us on the Earth at the equator, and we're spinning real fast. Well, if the Earth spins fast enough, we're going to fly off. But we don't fly off. But this is the one to think about. I always do the Earth because we weigh, like let's say, like I weigh like 100 and don't know, don't yeah. Well, anyway, weigh like 150 pounds, and at the equator, I'm going to weigh 8 ounces less. That's just the take-home point. There is at the equator because things are spinning. Things are just going to fly off a spinning object. So that just boils it down to just basics. If you got something spinning like a saw blade, all the teeth just want to fly off the saw blade. Okay, even here, if you got something rolling, uh, and then this is going to pick up speed because gravity, you know what I mean? So it's just a circle, and then you got gravity. Once it gets to here, gravity is going to be like, hell yeah. Okay, so then we have to do with the free body diagrams. But anyway, if this thing is just resting at the top, it ain't moving. So it's got to be just slightly off center. So that's what we're going to do. We're just going to put it slightly off center. Oh, well, they put it right here. Okay. And then normal forces are kind of interesting. It's like if you're standing on a 45-degree ramp, the normal force is actually 45 degrees, to you. Like the actual like if you this is so interesting. Like let's say you take a scale and you're like, damn it, I want to lose 5 pounds. Well, just put your scale on a slope about 15 degrees, 20-degree slope. I mean, put some chalks on one side of your scale, then hop on. And guess what? You weigh less. You're like, why? Well, because there's no the downward force into that scale isn't downward. It's at an angle, and then so half the force is going into the side of the scale, and it works for scales. It's kind of interesting. You're just like, well, I can just lose 5 pounds just by tilting my scale at an angle. That's crazy. Okay, same thing here. So normal force is always like if this is the angle right here, the normal force is always perpendicular to that angle. Booyah. Your gravity is always towards the center of the earth. And then this is just like a sculpture. This is just a circle. This ain't the earth. This is just like a sculpture with a small little steel ball that's about ready to roll off. So the mg, the force of gravity is always just straight ass down. So okay, perfect. And okay, so it's not moving right here, and guess what? It's moving a little faster, moving a little faster. So you got this acceleration in the tangential direction. Well, it's going that direction. Hell yeah. And we always have to know that when things are going around a circle, the acceleration is towards the radius. Because, like, let's say this is just a saw blade. The tooth is now here, the tooth is now there. It must have moved. Like, the teeth just want to fly off in straight lines. But because the teeth of the saw blade are still attached, they actually have to move, they have to accelerate towards the center. So that's spinning in a nutshell. So this is always towards the center. Now, for this problem, what do you call it? I mean, are you calling like flying off? Is this the positive direction, or is this the negative direction? See, right here, they say towards the circle is the negative direction. And I don't like that. I like to keep it simple. Well, when you're dealing with circles, like this is farther away from the center of the circle. So I don't get that. That's the one thing. It's like I don't know. It's just me. With circle problems are so hard in. This is the origin. This is 0, 0. This is positive. This is more positive. This is more positive. So if we did it that way, the uh the normal force should be in the positive. It should be positive. Force is positive, and then minus mg, and then but it'd have to equal to negative, just like we said. This is negative. See, it's going towards the zero. If this is 0, 0, this is in the negative direction. So that's the only thing about this I don't like, because circle problems are hard enough. You know what I mean? This acceleration towards the center is just classically always negative r omega squared. So if we put a negative mr omega squared right here, well, that means we have to put a negative here and a positive there. Exactly. Yeah, yeah. See, this is in the positive direction. This is in the negative direction. Now, if this is our origin, look at this. Look at this. Our gravity is over here. Our gravity is straight down. So the only component uh, towards the center of the circle, towards this NA, is actually well. This is if this is the angle, this is sunshine and sine and this direction, and then cosine is the hoodlum, just kind of adjacent in the alley, adjacent. You know what I mean? So that's a mg cosine theta. So it's ng is pushing up, and then just minus mg cosine theta. So I would switch these. I would make this positive, normal force acting up, mg cosine acting down is equal to negative mass times acceleration. Well, we said the acceleration is negative r omega squared, but this is basically F equals ma. Find the forces equals to the mass times the acceleration. We know acceleration of a circle. And then booyah, this is the only one we really need. No, it's not. This is absolutely not even the one we need. This is the one that's going to actually answer the problem. Like the solution to the problem is like, guess what? When this thing flies off, is there any normal force? Is there any force touching the circle? No. So that's going to be our constraint, is that when this is 0, well, and that doesn't matter what the sign is. This would have been negative. This would have been negative. So who cares? If this is 0, the signs don't even matter. Actually, the mass don't even matter. So you basically have something that looks like g cosine theta is equal to r omega squared. So that's going to answer the question. And what the hell does that even mean? Well, it means that at some sort of angle, this is the velocity. This is see, it's like 0 velocity, and then hell is picking up some angular velocity. You know what I mean? And this is just true velocity. This is in radians per second, but multiply by this radius, you actually get the true velocity. So basically, the true velocity squared, essentially, but it's not the true velocity squared. It's the radians per angular velocity. But when the angular velocity squared times the radius is equal to the angle that it's at, cosine of that angle times gravity. Hell yeah, that's the sweet spot when this ball flies off. And again, like we said, back to here, it's 82 degrees. Now, how did they do it? You know what I mean? Who cares? No. I'm joking. But they do another one because hell, we did F equals ma, and this was in the normal direction. Now we can do F equals ma in this direction because gravity acts this way. Hell, so we got a little component in that direction, and that's here's your angle, here's your sunshine, and so this is mg sine theta. So this mg sine theta, we found the forces. They're in, let's say, yeah, we're just going to call this the positive direction. Things are going this direction, so we're calling the clockwise direction positive. So forces mg sine theta in the positive direction is equal to an acceleration. Yeah, it's zero velocity here. It's more velocity. It's hella, and it's flying off. So the acceleration is that way, and that's mass times acceleration. Acceleration in the tangential direction is just radius times the angular acceleration. Which what the hell is angular acceleration? Well, that's just the change in angular velocity divided by the change in time. Okay. Anyway, that's F equals ma. Booyah! And this is the one that we're going to use. Mg sine theta is equal to mr alpha. What they do? Well, they use the fact that, oh my God, they have to integrate. So you can solve this one. I'm not even going to do it. I'm going to show you why. That's where I jump in, and that's why we're going to go to Excel. Because you can solve all these F equals ma's problems like all the same. And so you have to get your Greek letters. How the hell do you get your Greek letters? Well, you go here, and then you go home. You go insert symbols, symbols. Hell yeah, go to Greek right here. Just Greek it up, and then you got them all. You know what I mean? You want a phi. You want an angle phi. We don't need an angle phi. There you go. You can insert an angle phi. We just did it. Okay, get the hell this out of here. Okay, anyway, and we have our variables. Basically, for this, we're just going to use mg sine theta mr alpha. So mg, our radius. We're just going to say the mass is 1, radius is 1. It makes everything kind of just simple. Just one meter. It's a 1 meter circle radius. So it's a 2 meter diameter. 1 kilogram is the thing that's rolling off. Fair enough. Okay, and then G is 9.8. We're on Earth. Okay, you can do this on the moon if you wanted to. Holy Toledo. Let's do it right now. Check, because we just did it in Excel. I think what the hell is moon gravity? 9.8 divided by 3. Is it divided by 6? Is it 1/6? Is that just how you do it? You just go equals 9.8 divided by 6. Is that all? Oh, that sucked. That did not work. Whoa. No, 9.8 divided by 6. Okay, there you go. Whoa. Is that right? The gravity is less? This thing's flying off at, well, let's go to a more accurate one. This thing's flying off at 2 degrees? No way. On the moon, this thing's flying off at 2 degrees? I don't know why it would, because it seems opposite. But anyway, let's just go back to our problem. And hell yeah. And so our answer is, well, that's a rough guess, but 48.2. Here's better guesses, 48.2. And what's the actual answer? Right there, 48.2, right there. Booyah. All right, so we can get these out of the way. We just leave them around just for now. But anyway, okay. So this is how you set this up. We need our. So you're gonna have an angle. Okay, that's the first thing. I like to do it just like distance, velocity, acceleration. So I put the angles over here, and you can't make this 0 because here's our angular acceleration. What's sine theta? Well, when this is right at the top, theta is 0, but then sine theta is 0. There is no angle. It's just resting up there. So it needs to be just off kilter, just a touch, and 0.01 radians. Okay, but we need a lesson in radians. What the hell's a radian? Well, a circle has 2 pi. It's got 6 radians all the way around. So let's count them out. So here is 1 radian, 2 radians, 3 radians, 4 radians, 5 radians, 6 radians. Okay. And the other thing that you need to know is 1 radian's about, well, what's about 60? Did I even do that right? No, I didn't. How many radians in a circle? Isn't there 6? 1 radian, 2 radians, 3 radians. Yeah, this is 180 degrees. Yeah. So, this is 45. So this is 60 degrees. 60 degrees. So 1 radian's about 60 degrees. It's 57 degrees, but it's about 60 degrees. There you go. So there's 60 degrees. I'm getting confused because that's 90. That's 90 degrees. So this is 1 point, pi divided by 2. It's like 1.5 radians. Who cares? Uh, but 30 degrees, let's say this was 30 degrees. This is 0.5 radians. Okay, this is 60 degrees. That's 1 radian. Okay, and we said that about 45, 48 degrees is going to fly off. So all we need to do is figure out between 0 and 1 radian. Okay, fair enough. And that's exactly what we did. Now, between 0 and 1, well, we need to start by like 0.01. And now we have 100 increments in between 0 and 1 radian. So that's why I chose 0.01 radians. You know what I mean? If that made any sense at all. But yeah, no one knows radians. Well, let's say this is 0 to 48 degrees. Perfect. You would just throw 1 here, and then you would change it to, and we can do that. You know what I mean? Like, well, because what's the conversion? Well, if this is in radians, you take that, times, there's 2 pi radians. So 2 times pi, and then divided by 360. So there's 2 pi radians. There's 6 radians in a circle. 2 pi radians in a circle. Hell yeah. Oh, whoa, whoa. Sure. I think we got it right. And then there you go. There you go. And we'll just throw this all the way down. Booyah. So let's see. Did that even work? No. Damn it. I don't know why that didn't work. So we're just gonna. Oh, duh. Duh, 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 duh. Oh, no. We already did this one. Oh, this is in radians. And yeah. So if this is in radians, where we're gonna go equals this times, we got to go 360 divided by 2 pi. But it's just easier to go 180 divided by pi. All right, booyah. But anyway, so yeah, 3 radians. I don't know. That's yeah, that's 180 degrees. Isn't that kind of what we said? Hell yeah. So we said there's 6 radians in a circle. So even just right away, this was our anyway, we'll get to what the hell we just did. But yeah, you can take this all the way down. Booyah. All right, there you go. So yeah, 48 degrees, 49 degrees, 0.5 radians. It's always a good one to know. It's 30 degrees. And then guess what? 15 degrees is 0.25 radians. There you go. See? So now we're learning about radians. That is, you need to know that. Else it's just not going to make sense. Okay, so booyah, we got our radians. And we're just going to start with 0.01. Now, this thing ain't moving. So we're going to start with 0 radians per second. That's our velocity, basically. I threw in this column. It'll be helpful in a second. But here you go. Here's your angular acceleration. And isn't that the equation that we, you know what I mean? Look at this. Angular acceleration is equal to mg sine theta divided by m divided by r. So yeah, we just did the g divided by r sine theta. Exactly. There you go. G divided by r sine theta. So you just type that in. So we're basically G 9.8, R 1 meter, theta. And then you have to see how this has dollar signs. You click right next to it, and F function 4 F4 puts dollars. So you want 2 dollar signs on both of them. Whoa, 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 whoa. F4. I don't know how Excel works. You got to click, then click off things so it doesn't just destroy the whole universe. All right. So anyway, so this is the take home. Booyah. You get your angular acceleration because you got the equation for it. F equals ma. That gives you the equation for this. Okay. And then what is angular acceleration? Well, here it's change in angular velocity divided by change in time. Okay. So look, I just solved for change in angular velocity. Change in angular velocity is just this acceleration that we found times the change in time. So here. So for this one, our change in time is just 1 second. You know what I mean? Because we thought we could get away with just just doing this real simple. If this is our angular acceleration, 0.1 radians per second every second, well, in 1 second, our change in speed is going to be 0.1 radians per second. Okay, cool. and then we type that in right there. Look at that. So our initial speed times our change in speed. Okay, fair enough. So that's that right there. Now, the thing was at rest, and then it got up to this speed. So we need an average velocity, because it wasn't this velocity and it wasn't that. It was slow, and then it got faster, and so we take the average. So to do that, you take this one plus this one, divide by 2. All right, I think we can handle it. But still, that might be too much for some people because you need this average velocity now because our average velocity was 0.05 radians a second. Well, guess what happens in 1 radian? I mean, guess what happens in 1 second? Our radian goes from 0.01 plus 0.05. So it goes to 0.06. So this is our equation here. We start with 0.01, and then we add our average velocity times our change in time, and we get this change in radians. Booyah. Since we got a new radian, we got a new acceleration. Booyah. So you type this in. You know what I mean? And our new acceleration is 0.58. 0.58 what? Well, definition of acceleration is change in angular velocity divided by change in time. But we said our change in angular velocity. Well, that's just the acceleration times our change in time. We're using change in time at 1, so we're just keeping it real simple, real dumb, and this is going to be over real fast because it's just such a lousy guess. But anyway, yeah. So angular acceleration times 1 second. Well, that's going to be it's going to change by 0.58 radians per second. So now here, look, you go from 0.1 radians per second plus 0.58, and that's how we got that number. And get your average. Well, what's the average between 0.1 and 0.68? Sounds like 0.39, and that's how you do it. Add them together, divide by 2. So super simple math, but you just got to do it, and then can you figure this out? What's your new radians? Well, is your old radians plus your average velocity times your change in time. Okay, fair enough. And then you do this until your radians just get stupid, and just ridiculous. You just went from 25 degrees to halfway around, and but anyway, so let's do this again. So for this one, our change in angular acceleration, our angular velocity was going to be this A times change in time. And guess what our change in time on this one? Well, now we're using a smaller change in time, 0.01. So instead of just and the other thing I should say, once you get this, then you can just take these and then just bring it down. You know what I mean? And then it puts them all in there. And I don't know why I got rid of that. But anyway, so get rid of that. So here you go. So we do another one, but we use the change in time to be 0.1 second. And then the only other thing is right here. When we try to find our new radians, it's our omega average or our speed, our average radians per second times our change in time. That gives us our change in radians. And why is that? Well, look at this. Angular speed, angular velocity is equal to change in your angle divided by change in time. Okay, sweet. So we can solve for change in angle. Therefore, the change in angle is equal to your speed, and this has to be average speed for that change in time. That's why we did this column for the average speed, because you can't just take the slowest, you can't take the fastest. You would be off. It's the only time that would be off. So hell yeah. But those are this is the only 2 equations we're using. Now, they use those 2 equations. They used them right here. So I'm just going to circle them. You can read through what they did. But you have to do this to separate variables and to integrate. And I don't know. It's just going to confuse you. So you might as well do a chart because you just, I don't know. You actually have every angle and every speed. Yeah, we do this, and then let's go to the bottom of this. Hell yeah. So it didn't take too many iterations. And then we already get to that 57 degrees, one radian. Okay, then we stop. Why do we stop? Because we do these two columns. Now, what the hell are these two columns? Well, like we said over here, when your normal force is 0, mg cosine theta is equal to mr omega squared. So here's mg cosine theta should be equal to mr omega squared. So we run these two columns, and guess what? Right here is where they're going to be equal. See how this one's higher, this one's lower, this one's higher, this one's lower. Hey, guess what? This one's lower, now this one's higher. So somewhere in between 43 degrees and 57 degrees, this thing flew off. See, so even right here with the change in time of only 0.1 second, with a change in time of only 0.1 second, it's still not that accurate. But when you do these, even if we weren't doing circles, acceleration, velocity, position, it's kind of cool when you do it in Excel because, yeah, this change in time comes in two places. So if this is our angular acceleration, that means that our change in angular velocity, well, that's going to be our angular acceleration times our little change in time. Okay, booyah. So we get that. And then we find our angular, our speed, our angular velocity, our angular speed. We can find our average angular speed. And now we can find our actually change in angle. And then we have to take the original change in angle plus the average speed times that change in time again. So the whole take, why did I go over that? Because this change in time shows up twice. So it shows up here. You multiply by this change in time right here, booyah, and then you multiply right here by this change in time. So that you will use that change in time twice because this is change in velocity, this is change in angular speed divided by change in time. This is change in angle divided by change in time. Okay, so that's where that time component comes in twice. Now, you just need to do this, it's nice to just get an it's like, hell, that's close enough. It's going to fly off between 43 and 57 degrees. Did not know, now I do know. And it didn't take me too long. But we'll have to do another one because, and then here, so here we use 0.1 second. Well, guess what? We did it again, and then we use 0.01 second. And, looks like we get we get an average between 47 and 49. So our average is 48. And then right here, we do it again. And then we get 0.001. Hell, 48.2. Isn't that the right answer? Hell yes, it is. And we come over here, and we did one more. And we got 0.0001. And it's basically 48.2, 48.2, 48.2, final answer. But look how many, look at this. 16,434, Excel things, but all you have to do is just, you can't even get to the top of it without using some cheats, you know what I mean? Cheat codes just to get to the top of here. But anyway, this is all good in the hood because, booyah, you got that. You type that in. You do your change in, with your change in time. And then you come over here, booyah, well, then you add these together because our speed was 0, and now, hell yeah, it changed a little bit because acceleration. And booyah, you get our new speed, and that's just going to bark at you the entire time. Then you take your average speed, plus divide by 2, booyah, and then you figure out your new angle. And that's the most important. I don't know if it's the most important part, but it's your old angle plus your average velocity times that 0.00, times that time thing. Which for this one, hell yeah, we went crazy. 0.00001 maybe. And booyah! So you get your new angle. Okay, now you got to pull. Like you would. So for, and then you do these, you know what I mean? mg cosine theta, there's your theta, mg are up there. There's your mr. If you want to see where those values are, r's over there, m's over there. If you want to see where the mg cosine theta is, the cosine, your angle is just right there. Oh, all right. So your angle is just right there. and then there's your G, and then there's your M. Okay, but we're actually gonna do one of these, from scratch because like this took, look at this, 16,400 just, and most problems you can just, like, if it's a skydiver and you want to find their speed, you just do something like this, you know what I mean? And it's just real simple. You don't have to do like 16,000. It's because circles. It's because this is always changing, and it's just always changing. So the only thing not accurate about this is that, hell yeah, your acceleration, well, I didn't find an average angular acceleration. I just chose a point. I said, if this is my angle, this is my angular acceleration, and I'm going to say that this is the angular acceleration for a very short amount of time. And that short amount of time is but for this one, it's let's see what our time is, 0.0001 second. And so I'd say that's a very small amount of time. So I bet you we're pretty accurate. That's why this is accurate. And then that's going to be our change in angular velocity over that short amount of time. And then you add it to the original angular velocity. Okay, so we did it. Well, let's do it. We're gonna come in here, and we're gonna go shift control down, down, down all the way. Delete all this, and we're gonna do one from scratch. And then I got to get some food in me. Um, we have to type in 1 here, because if that took, here's how you do, like, we're just going to estimate. So let's say, so there's two, let's say this is like 100,000, 200,000, I don't know, let's just do 200,000. So we type a 1 right here, and then we go to I don't know why it's not doing this, but there you go. You type a 1 right there, go to fill, go series, go column, because this is a column, linear, step value 1, stop value 200,000. Did I even get the zeros right? No, because this is going to take a half hour just to do that. But there you go. So now you got to, well, now you got to 200,000. Booyah. So you got to 200,000. We're going to start this at 0.01. This one doesn't really matter. You don't, if you went down to 0.001, maybe you get a little more accurate. Do you want to do that? And we might have to, holy bloody hell. Sure, we'll go to 0.01 because our DT, our new DT, we're going to go 0. This thing's barking at you the entire time. It's crazy. I need a whole tutorial just to figure out why that's barking at me. Okay, there you go. So now we have a very, very, very small change in time. All right, so here, just from the base, we did no integration. We just set it up. Our F equals ma. And we got our A, our angular acceleration, and that's gr sine theta. So it's going to be equal to parentheses. G, you got to go F4, put those dollar signs, divided by R, F4, and then parentheses. I don't know if you have, I think you got to do, you got to put multiplication everywhere, else you're just going to scream at you. Okay, and booyah. And the other thing that we need to go, so I'm putting shift over. Now I'm putting control, and I'm going to go down. And now I'm going over here. I want to increase, like how many here? 1, 2, 3, 4, 5. So we need about 6 or 7. There's 6. Booyah, there's 7. And we're just gonna, well, oh, I think you do this. You go boop boop. Oh no, I didn't want to do that. Okay, but there you go. We will do that later. Okay, so now you got your angular acceleration, and look at these equations. There's angular acceleration, change in speed, change in angular velocity, change in time. So just the dw part. Well, I put it right here. dw is acceleration times dt. Just spelled it out right for you. So it's acceleration times dt. You got to put an F4 on this dollar sign. Okay, booyah, booyah. Okay, now guess what? This is 0. We started, or done it, well, sure, but just our original velocity is 0. Type it in. But now our new velocity, hell yeah, is our original velocity plus this dw, change in velocity. Booyah. Okay, but what's our average velocity? Well, that's going to be this one plus this one, parentheses, divided by 2. All right, hell yeah, we're on a roll. But now the other tricky part. So now what's our change in angle? Well, that's going to be our original angle plus, here's our average, times our change in time, and then F4 on that. Now, does this make sense? Because here, change in angle, omega average times change in time. Where did we get this? Because our angular velocity is equal to the definition of angular speed, angular velocity, radians per second. Well, it's just radians per second. It's change in angle divided by change in time. So if we just want to find the change in angle, but you just rearrange W times dt, W times dt, but it's got to be W average. That's the only little caveat. And now you might get a halfway decent answer, but it's got to be average. So uh, you only have to do like 3 things, you know what I mean? And that's it. Okay, so now here, we'll do this one too. So we got M, we got to do F4 times G, you got to do F4 times cosine. Now, I always thought this was pretty fast, but no, this is hella slow, and you'll make tons of mistakes. And then you got to figure out where the hell you made your mistakes because it's Excel. So anyway, F4, and then times R, F4, dollar signs, and now times your speed. Now, this speed is just right. This is your speed, not your average speed. This is the actual speed at this moment. Booyah. And then you got to square it. Pair it to the 2. Ho-ho. Booyah. And I'm just going to make sure I got dollar signs and all that jazz. And I do. Okay, so we're set. So now we're going to bring this down there. And then, oh, hell yeah. So now we can just do this. And we can go Shift, Control, down. Okay, so that highlighted. I don't know how far that highlighted. Well, did that highlight just to infinity? Oh. Yes, it did. It literally highlighted. And now Excel doesn't know what to do. So what we do is we come over here, you go down to this last number, you type we're just going to type an X right there. Okay, booyah. And then go up. And now, oh, we got to get rid of some of these colors. It's going to drive me nuts. So this is your fill. Okay, so we'll see, we got all of our things in here. But now, look at this. See, now we got a catch. So what the hell did I do just right there? I went right here, and then I pushed Control, and then went down. Now, we're going to go Control up. Now, what if I did right here and went Control down? It's going to go to the bottom of Excel. Go right here, go Control up. It's going to go to that X. Okay, Control up. So we're just making little spots to catch. So now when I do this, and then I go Shift, Control, down, it's going to catch right on that X. You can go up just to make sure it's doing the right thing. But now we're going to go to Fill, and we're just going to fill down. And I think that'll do it. And it's gonna take a while because what we just asked it to do, it has to do like so many different times. We probably just should have started with to see if it even, started with like 5. See if that was even what. Yeah, Excel is not responding. So I'm just gonna wait here. It's 1:33. I'll have to edit the video, so catch you on the other side. Oh hell yeah, hell yeah! We didn't even need to like edit anything out. So booyah, it did it. There you go. And we're gonna go all the way down. And no, we need more though. See, look at this. Our radians is only 0.26. See how we actually need to get this up to 0.26. But now that we're down here, you can take your toggle. That is the nice thing. Okay, so we need hella more. So we're gonna go here. We're gonna go. This was 200,000. We're gonna go Shift because I don't even know how to do this no more. So we're gonna go. Just delete that. Oh no. So we're gonna go here. We're gonna go Shift up, and then just delete, and then Control up. We're gonna type in a 1 here, and we're going to do that same thing. I guess you got to click it and then unclick it, then click it again. Go series, column. I don't know. Oh my God. How about just 1 million? That's Excel. That's Excel. Holy Toledo. Well, because it takes 20 minutes to do that. Damn it. Um, here. I don't want to do that. So we're gonna go all the way back down to here. Okay, so here we're gonna do another one. We're just gonna do another 100,000. You know what I mean? It's like asking for more chips. So oh, we got a lot of data on the board. Excel is just gonna, and I don't know why it always does that. It says there's like a cross reference. I don't think so. Okay, so we're gonna go fill, series, step value. Well, let's do the column. You got to have a column, and then linear, step value. We're gonna do another 100,000. 1, 2, 1, 2, 3. That's 100,000. Holy Toledo. Okay, booyah, got 100,000. So now we're going to go down here, put an X, control. So I'm hitting the control button, and then I'm going all the way up. And then we're going to go, okay, so we're going to highlight that just so you can see. And we're just going to, I'm going to do shift, control, and then, oh, what the hell? I think I need to highlight it, and then shift, control, and then just down, the down arrow. Booyah. And then fill. And then fill down. Booyah. So now it's gonna hopefully take less time. But no, it's probably gonna take more because there's so much data. But it just shows you that if you just want a real accurate answer, you can. You can spend about an hour waiting for Excel not to respond. And then all of a sudden it just pops all the data on the screen. All right, it's 136. I'm going to catch on the flip side. Oh, hell yeah. Oh, hell yeah. All right. So we got some big numbers over here. So you just click up here and then just double click the columns and then it should, perfect. Okay, hell yeah. And look at this. Look at this. So we're already at 3.9 radians. Now, what the hell is that? Well, there's 6 radians in a circle. So we're already past 180. And for the love of God, if it shows me that 5 more times, I'm just going to lose my mind. Okay, but hell yeah. All right, so we're trying to find the actual answer, which is like 0.84. It's 0.841 radians. And if you don't believe me, we're going to go all the way to the top and whoa. All the way to the top over here and here's the answer. So there's the answer, 0.841 radians. All right, so now we're going to go, I guess you can always just go control home and then, but anyway, we're going to go down. Okay, we're going to go to here. Oh, I guess we got to go all the way over. Okay, yeah, we're all over. All right, so we're going to go 0.841 radians. Ooh, this is touchy. Oh, there we go. 0.841 radians. Oh, this answer is going to be so accurate because here you go. 0.533 is bigger than 0.532. But guess what? 528 is not bigger than 0.54. Oh, so it's right here. The answer is right here. So 0.532 is not bigger than 0.534. But 0.533 is bigger than 0.5331. 0.5332 is not bigger than 0.5. So there it is. Booyah. And I'll have to, I mean, that's like splitting hairs, but there you go. See how these numbers are bigger? 5339 is bigger than 5332. So we got 5333 is bigger than 0.5331, but 0.5332 is not bigger than 0.5334. Okay, and look at this. So there's our answer. So we're going to do this times 180 divided by pi. I'm just going to tell you that. But how would you actually do that? Let's do that one more time. How you convert in radians? Well, so you got radians. Let's say you had 6 radians. Well, you would multiply by 360, then divide by 6, and that would give you 360 degrees. Why would you, if you had 6 radians, why would you multiply by 360 and then divide by 6? Well, it's because you're multiplying by 360 degrees in a circle, but then you're dividing by 2 pi. That's 6. 2 times pi is 6. And that gives you that answer. Uh, hopefully. What the hell? Oh, it didn't like that at all. It should like that. Why is it missing something? I don't think it's missing nothing. Oh man. Okay, this is why I just do 180 divided by pi, and I don't know why it likes that, but hates the. There you go. Well, why did it not like me do 2 times? Why did it not like that? That's so bizarre. Why doesn't it like that? Okay, it liked it, but we need to get our 360. So yeah, 360 divided by 2 pi, that's how you do it in Excel. Holy Toledo. I don't like using pi in Excel. I don't like using angles in Excel. You have to use radians. But it is good. All right. Uh, why doesn't it lock? Okay, there you go. And our answer is 48.2. So there's our answer. Hell yeah. And when so now you can do this. We're gonna go shift over and then control down, delete all that. Yeah, perfect. So now it took 237,763, but hell yeah, we got a very, very exact answer. And the only thing about this problem is I wasn't, because I just don't, my calculus game isn't very good. But what I wanted to figure out is what the time was. How much time did it take to get here? And once you just take like basically all the units in this, man, that's for another video. I think you would just take, well, because our change in time was like 0.00. Yeah, what was our change in time? There you go. We're just gonna do that. Come down here. So dt equals to paste it in. Paste that. Oh, I guess I'm not able to. So it's a 0.0001. 4 zeros and a 1. So our change in time, our dt is equal to 0.12341 seconds. Okay, there you go. Booyah. Oh, what up? Okay, there you go. And we're gonna go shift up, control up, and oh yeah, that's for another video to figure out if we can actually figure out what time. I would imagine the time increment, like each of these was one of those time increments. So then we can figure out how long it actually takes. But what I couldn't back it up, I just don't know my calculus enough to be like, well, shouldn't we be able to integrate for time? Because they didn't integrate. They got rid of time on their integration. But it should be real simple just to integrate for time, it seems, but maybe that's not. Maybe that's not simple. I just, that's why I use Excel, because my integration skills, I need to see it. I'm a visual learner. So, if we're talking change in time, well, hell yeah, we just make our change in time real small. That's exactly what integration does. And hell yeah. And we went through all the steps, and you got to learn how to do like hella long, uh, holy Toledo. I mean, if you have to throw in a lot of values just to get an accurate answer, we did it, and I think we're done. Yep. So, Well, where's the other sheet? All right, there it is. Yeah, we'll just get it buttoned up to see if I have any last words. I don't think I do. I like the way we did it, and so what we did was we took an F equals ma problem. We solved for this acceleration, and in this case, it's angular acceleration. So we got all the other terms to the other side. Your masses cancel. Your radius goes under that g. So that's exactly why we got this g sine theta. G divided by radius sine theta. And once we got that, hell yeah. Then we put the wheels into motion because all acceleration is just change in speed, and all speed is just change in position. So it's a circle problem. Your position is your degrees in radians, and that's kind of confusing. Your speed is angular speed, and that's kind of hard to say every time. And your change in angular speed is angular acceleration, and that's also a little bit hard to say and a little bit confusing. But it all works out. And essentially, I'm going to do more of these. You just take an F equals ma problem. All these F equals ma problems, well, the integration can get kind of complex. Like it can be a second order. You know what I mean? And then you got to do some sort of little tricky trick right here, which they did. What they did, they took the angular speed is equal to, well, definition of angular speed, radians per. See, this angular speed is in radians per second. So that's just change in radians divided by change in seconds. Perfect. And then look at this, angular acceleration. Definition of that is just, well, what's the units on angular acceleration? It's radians per second per second. Well, what's radians per second? That's change in, that's angular speed. Radians per second divided by seconds. So angular acceleration is just angular speed divided by time. Change in angular speed divided by change in time. So then they took the change, because both these have dt, they made them equal to each other, and then they got this alpha d theta, and I guess you just solve for alpha and then just throw the whole mess right into there. So if you're solving for alpha, this is omega d omega divided by d theta. D theta goes over there so you can integrate. Omega d omega stays over here, and now you're going to integrate this side. So that's exactly what they did. See how the d theta went over there? Now you can integrate sine theta d theta. You can integrate omega d omega. So then you get omega squared divided by 2, simple integration. Integration of sine theta becomes 1 minus cosine theta. Booyah! So now you got this equation, and it involves speed. Now you know the speed. See, this equation, you just know the angular acceleration. For every given angle they give you, you can figure out how much it's going to accelerate, or what's acceleration. But now you have an equation that says, hey, for every angle, you can know its speed. So that's pretty cool. Every single time you put in the speed or your angle, you can find speed. And then it's just real simple for them to well, maybe it's not simple. No, it is. It is fairly simple because look at this. See how you have your speed right here in omega squared? Well, right here you have an equation. This is the equation that's the sauce. It says once this normal force goes to zero, once the ball don't feel the circle at all, it flew off. So you don't have any normal acceleration. You don't have any normal force. I'm sorry, normal force. And then so mg angle is equal to mr omega squared. But we got this equation that says omega squared's there. So then you throw all this crap into there, and that's exactly what they did. So yeah, you do it to it, and then you just solve for the angle. And then the angle is actually at that point, because this is 1 point, when your normal acceleration is 0, that's your angles right there is 0.841 radians, 48.2 degrees. So again, you would get this 2 over there. So you got 2g divided by r 1 minus cosine theta is equal to omega squared. You throw that into there. Well, now your r's cancel. So now you just got mg 1 minus cosine squared. And isn't that what we have right here? I don't know why they don't look the same. Um, Yeah, mg cosine theta. Uh, mg cosine theta. Well, your m's cancel. Your m's cancel anyway. So g cosine theta is equal to 2 times g 1 minus cosine theta. Your g's cancel. So now you just got cosine theta is equal to 2 times 1 minus cosine theta. See, I don't like how they and instead of 2g 1 minus cosine theta, they took the 2 down there. But yeah, the g's cancel. We already did that. And all right, my battery's running out of juice, but that's how they did it. But yeah, if you know, but this is just one point. But I guess you got the equations for everything else too. And yeah, maybe I should have actually done that. Well, if these are the equation, if this is the equation for speed, well, hell yeah, just solve for omega, which is just 2g divided by r 1 minus cosine theta, square root of all that, and that's what you would type in right here. Yeah, this equation right here, you would be like square root of 2g over r 1 minus cosine theta. That is the speed. So that's cool. And I mean, we just figured out the angular acceleration. And why did we do that? Because all these problems are easy when it comes to F equals ma. F equals ma, you can find the acceleration. Now, it's a humdinger to actually find velocity sometimes. It's a humdinger to actually find position. So that's why we do it in Excel, because the integration can be brutal. And one little mistake in your integration, you're not even close to the right answer. So it's nice to do it in Excel. So now you can double check. And if I was on point, and I will be on point for other videos, but we got to end this thing. I'm hungry, and it's already like 2 a.m. and I'm starving. Okay, well, thanks for joining me, and this was fun. I'm glad I did this one. And guess what? That's a video.